So I'm Andy Harris. I'm from Autodesk, from the advanced consulting team at Autodesk. So I'm just going to give you a little overview of Autodesk. So humble beginnings. We started with AutoCAD back in the 80s. And since then we've grown beyond that piece of software into all these different areas: media and entertainment, manufacturing. Basically everything you can think of, we've probably got some involvement somewhere. We have 16 million professional users, 225 million consumer users, and 680 million students and educators, and that's because the software is free, so there's lots of people there. So in the UK, we have a few locations. We have a construction R&D, we have our main headquarters in Farnborough, we have a few offices in London, and we have an office near here as well. So in Birmingham, we have the advanced manufacturing facility. We have a small advanced consulting group there. And then we have a large advanced consulting team in London. But advanced consulting is actually worldwide. San Francisco, which is the main Autodesk headquarters. Novi in Michigan, mentioned London and Birmingham, and we've also got a group in Singapore. So I'm going to talk to you a little bit about generative design. So this is currently a piece of software that's in tech preview at the moment. And the idea behind this is you define, generate, and explore. So you define your engineering problem, you then generate a large range of solutions, and then you explore those to find the best one. So this is a little image of the software. So we have a suspension upright here, or the necessary parts for that. We have these red bits, which are space claims, obstacles. The geometry can't interact with those. We have these green bits, which are the preserved regions, in this case the bearing housing, steering link, wishbones, those kind of things. And we apply our boundary conditions on there, and then we choose things such as manufacturing methods and manufacturing constraints. In this case, we've got over 40 designs here. To go through all of those could take time, and obviously the more options you tick, the larger amount of solutions you could potentially have. But the idea is all of these solutions meet your requirements, perhaps just with a different manufacturing method, a different manufacturing constraint. So we have this explore environment. In this case, I'm really interested in having a very stiff, lightweight design, so I'm looking down this bottom left corner. And I can interrogate these models a little more closely. So I've got a solution here, I've got a stress plot. And then I can download those. You can download the STL directly or download straight into BREP, so an SAT file. So what we use generative design for is we're looking at comparisons between materials, manufacturing constraints, structural loading, CAD generation, and then sometimes we combine that with NetFab to do beam and lattice generation. But the main thing is this exploration of designs. It's there to help you design, get through that concept stage. So from those designs we looked at before, we have 3 different solutions here, in this case 3 different materials. It's just a little angled view. You can just see some of the differences that you get. So this is another part that I designed last week. We designed this for the Automotive Innovation Forum. And this is a car wheel. In this case, we've got the hybrid design here, where we're taking that generative design and also combining with NetFab to do the latticing inside. We can apply this not only to high-end products, we can apply this to more consumer-level products, such as a BMX bike. So we've applied additive manufacturing to this part here, where we've applied AGD with some manufacturing constraints. And then here we've actually got a different solution where we've got a glass fiber reinforced polymer FDM printed component. So I'll just go through the images, and I've got a video of this. So next I'm going to give you a little overview of lattice optimization. So if you've been to our stand, you'll have seen the seat frame. So the one you've seen out there is one of our earlier iterations, and it's slightly scaled down. This is actually the full-size part. It's around this size. Actually, for an aircraft, if you ever look under the seats on an aircraft, you may see something like this or something resembling this, but without the lattice, of course. So the idea behind lattice optimization is inspired by biology, the human body. So we have a femur bone here, and within that we have this porous lattice-like structure that's got varying density and thickness. And then we have the skin that's going around the outside, which is also varying thickness. So it's a really lightweight and stiff way of designing. And it does this by basically manipulating the geometry to pull it away from what is just a simple bulk material property. So you're able to particularly end up with the lower density, higher stiffness, particularly in the bending stiffness. So the way NetFab does this is you can manually go in there and optimize, and you can apply bounding conditions and look at stress and strain and things like that. But you can also link this into Nastran, which is built into it, and it will automatically resize those features for you. You've got to be careful when you want to use lattices. You've got to think about why I'm using a lattice. The benefits are thin wall structures. You get limits to crack propagation. So if you think of a solid block of material and you get a crack in there, it can propagate through that component very quickly. A lattice, it will just arrest it as soon as the beam breaks. It doesn't go any further. You can get a high second moment of area. So you get high bending stiffness. You can get a lightweight solutions, typically with very good topology optimization. We're pushing 30, 40% mass savings. If we do latticing on top of that, we can push maybe another 10 to 20% out of the component. The other benefit is you get lower deformation during additive manufacturing. So we're talking about thermal distortion in the part is much lower. And as I mentioned before, we get control over that structural behavior. So this is the process that we use to design the seat frame that we have on our stand. So in NetFab, we're able to take in a component. We can choose the areas we want to put the lattice in, the areas we just want to keep them as solid, and the bits where we want to apply a skin. So for the lattice, you can choose a lot of different lattice topologies, a lot of different lattice unit sizes, and you can also choose the range that it optimizes between. And this is just an example of how the thickness can change, and you can have variable thickness, so it's not resizing all of the cells. You can just resize some of them relative to the others. And then it's exactly the same setup with the surface, so you're optimizing the thickness. So you should see what it's doing as it's optimizing, it's resizing those beams, it's resizing the thickness of the skin. This is all linked into our Nastran solver that's driving this. So how I set this up in NetFab, I can use a custom boundary condition file where I can use very, very high-end model setups, but in this case, we don't really need that. I've actually got a symmetrical boundary condition, so we're simulating 3 seats with 2 frames, and so then we're optimizing that frame for the EASA standard load conditions. Once we're happy with how it's optimized, we're able to then just do a verification on that, where we pack very fine tetrahedral elements in there, and so we get a really good idea of what the actual stress and displacement of the component is. So manufacturing this part. So this part is too big for most printers. I think perhaps concept laser could just about do it, but economically it's not really viable. So we applied a process of 3D printing the pattern. There's lots and lots of printers you can use. You can use very basic consumer level printers and also very, very high-end printers. The performance of this affects how good your final part comes out and how likely you are to not have a failure in the shell. So we used a PMMA powder, and we use the voxel jet printer. And we go through this process of printing a pattern. We can assemble a mold if we have lots of these parts. And then we go through applying a coating, burning that out, but I'll show you the pictures. So this is the voxel jet printer. You can just see a slight outline of the seat frame there. We tend to print all the channels in there as well to help the material flow. So you can see that here. So we've got that pattern which has come out of the machine here on the left, and it's got all those channels printed in there, and it's all ready to go. So the next step is actually to dip this in a slurry. So it's a ceramic coating applying to it. And then we do a quick sand coat on that. We autoclave the component. And then we burn it out. This is where your choice of design and material that you use for your pattern is very critical. If you have a plastic that expands too much, it will crack that mold. So you need something that's not going to cause that mold to fail. And then we're pouring in the material. In this case, we're pouring in magnesium. So that component you'll see on our stand is made from magnesium. And then we've got a D-shell. So this is where you've got to be careful with lattices. You can cast maybe 1 or 2 cells thick in lattices. Start going more than that, then D-shelling becomes difficult. So you end up with the shell stuck in the middle, potentially. And this is what happens if you use a material that is incorrect, expands too much, or you have a feature that is basically too large of a lattice, too small of an opening in here. The shell couldn't get thick enough, so it structurally is not strong enough to withstand the loading when the plastic expands, when it's burnt out, or when the magnesium is poured in. And you end up these plugs where the magnesium leaks. So the first iteration we did, we saw these. So we kind of went back to the drawing board and created this sample where we were looking at what is the lowest we can get away with and what is the thickest we can get away with. So here you'll see there are some broken beams, perhaps they're not formed properly, and then up here you'll generally end up with the plugs. So we have this happy middle in the center that we then redesign that component to. And then we ended up with this one, which has 0 flaws. And a lot of these we actually CT scan as well. So that's one of the extra benefits of investment casting, is you don't generally get internal flaws. So that's everything.